Last week, after a 3.5-year road trip and a more than 6-month surveying project, the Japanese spacecraft Hayabusa II successfully shot an asteroid. Yes, with a bullet. But that wasn't to protect itself or to save the Earth from Armageddon or anything. It was to kick up a sample of the asteroid's surface in order to collect it and bring it back to Earth. It sounds like a straightforward way to learn what the rock is made of, but when push came to shove, things could have gone pretty poorly. Hayabusa 2 is a follow-up to humanity's first asteroid sample return mission, Hayabusa. That spacecraft visited a stony asteroid called Itokawa in 2005 and returned to Earth with a very small sample of dust in 2010. For this mission, the target was Ryugu, a primitive carbon-based asteroid with an orbit not too far from Earth's. It has a different chemical composition than Itokawa and likely hasn't changed much since it formed at the beginning of the solar system. So studying it, and space potatoes like it, can help us unlock our history. Except there's a lot we're still learning about these kinds of missions, so Hayabusa 2 didn't go exactly as planned. For example, the sample collection was originally scheduled for last October, but once we got to the asteroid, images revealed that its surface was way bumpier than anticipated. So the team needed longer to find the best place to touch down. And even when they figured that out, the touchdown itself wasn't all smooth sailing. It actually happened around half an hour before mission control expected it to, although the Japanese Space Agency didn't mention why. That could have been a huge problem, especially since they instructed the spacecraft to approach Ryugu faster than they had originally planned. But the good news is it didn't crash. At 45 meters above the asteroid's surface, Hayabusa 2 automatically paused its descent, then reoriented itself for the remaining stage. But that required moving one of its antennas, and it could no longer send readings to Earth, which meant that all we could do was sit and wait for a signal that the craft had started getting closer to Ryugu to confirm that touchdown was happening. The moving antenna was always part of the plan, but that didn't make it any less nerve-wracking. Still, it all worked out. After getting Hayabusa 2 back in the right position for communications, Mission Control could confirm that the command to fire its bullet had been completed. We won't know exactly how big of a sample it collected until the spacecraft comes home, but there's a good chance we got something. Hayabusa 2 is scheduled to leave Ryugu late this year, but not before collecting at least one more sample. This one will be from below the surface, which will require the craft to make a small crater using explosives. If all goes well, these samples will return to Earth in 2020 and will provide data for decades. And this isn't the only sample return mission humanity is working on either. NASA's OSIRIS-REx mission will sample the asteroid Bennu in mid-2020, and although it's still in development, NASA's Caesar mission could arrive at a comet in 2029 if the space agency decides to move forward with it. So it's safe to say space potato sampling will likely be a little more common in the future. And speaking of space potatoes, how do you like that transition? In 2013, astronomers accidentally discovered Neptune's 14th moon hiding in pictures that the Hubble Space Telescope took last decade. But since the moon is so far away and hard to study, the first scientific analysis of it was only published last week in the journal Nature. And that finally allowed the International Astronomical Union to give this thing a proper name. Hello, hippocamp. It sounds pretty goofy, but the name comes from a half-horse, half-fish creature from Greek mythology. And all of Neptune's small moons get named after mythological water creatures or figures associated with Neptune or Poseidon. At only 34 kilometers across, Hippocamp is by far Neptune's smallest moon. It's also super close to the next moon over, called Proteus. It's less than 12,000 kilometers away, which actually raises some questions. See, Hippocamp is also about 1,000 times less massive than Proteus. So according to the general rules of orbits and gravity, Proteus should have either thrown Hippocamp out of Neptune's system or merged with it. Unless, that is, Hippocamp is a literal chip off the old potato. Astronomers hypothesize that this moon may have formed several billion years ago, when something like a comet struck Proteus and broke off a piece of it. Or maybe the collision threw out a bunch of smaller pieces in the same general area, and they collected back into a tiny new moon. Either way, there are a couple pieces of evidence to support this collision idea. For one, models suggest that Proteus has been slowly migrating away from Neptune over time. And billions of years ago, it would have been roughly where Hippocamp is now. Also, we've detected a huge impact crater on Proteus, which is more than large enough to have come from a collision that would have made Hippocamp. As always, scientists will need to keep investigating to say anything for sure, but one thing is obvious. Hippocamp backs up our previous idea that the Neptunian system is chaotic. It might look all peaceful from a distance, but the area around Neptune is kind of like a giant orbiting traffic jam. For example, we know that the planet captured its largest moon, Triton, after making its first generation of satellites. So when Triton rolled in, it disrupted everybody's orbit and caused all kinds of collisions. We also know that activity from comets has obliterated a bunch of moons. In fact, the team studying Hippocamp estimates that it has been broken apart and reformed 9 different times over the past 4 billion years. So this new study helps reinforce what we've already suspected. And as a bonus, the team studying Hippocamp was able to release new data on the other 6 small moons inside of Triton's orbit. That included data on Naiad, Neptune's innermost moon, which hasn't been seen since Voyager 2's flyby in 1989. So in addition to saying hi to Hippocamp, these scientists are helping us better understand the evolution of our outermost planetary system. Between this group and the Hayabusa II team, it seems like everybody is learning about the solar system's evolution these days, and we're pretty excited about it. Thanks for watching this episode of SciShow Space News. Since we haven't sent spacecraft to Neptune in about 30 years, there's a lot we're still trying to understand about the planet. And while the Hubble Space Telescope can clearly do a lot, it can't do everything. If you'd like to learn what mysteries we could solve with the Neptune orbiter, you can watch our video all about it.